Good evening and good day, depending on where you're joining us today. Thanks for joining us for this session on optimizing price performance using Azure SQL Database. Today, our presenter is Morgan Oslake. He is a principal program manager with the Azure data team. And with that, I'm going to hand over to Morgan.
Thanks, Elaine, for the introduction, and welcome everybody joining this session on Azure SQL Database. We'll be focusing on what serverless is, when and how to use it to best price and performance optimize your SQL workloads. But before we describe the serverless solution, it's useful to step back and highlight some of the challenges facing developers when price and performance optimizing their database workloads. Consider a typical scenario of an IoT application with a centrally managed database that receives rainfall data from thousands of geo-distributed weather stations. Also, further suppose that the database exposes endpoints that allow users to connect to it to run analytics scenarios as well as generate reports. Now, you can imagine when the weather is calm, that the workload demand on the application is relatively low. But then when a storm system passes through, that workload demand can increase rather suddenly. So in a sense, there's a correlation here between storm activity and workload demand on the database. The key point to emphasize is that the workload demand is unpredictable, both in terms of its amplitude as well as its timing. This presents DevOps challenges in terms of how best to allocate resources in order to achieve your price and performance goals. One option is to over-provision resources in order to satisfy peak workload demand. But then given this kind of usage pattern, that leaves much of the time left over for relatively lower idle usage, which represents wasted resources and ultimately higher costs. Alternatively, you could slightly under-provision resources, say to match the average usage over time, but then of course you would risk poor performance during peak usage periods. And then finally, you can build rescaling automation, particularly if you're already in the cloud and can take advantage of that elasticity. But that automation involves extra development cost as well as added operational complexity. That's exactly the kind of problem that serverless is intended to solve. It essentially provides two capabilities. The first is its ability to automatically scale compute. Here, the customer, the user, is able to specify a compute auto-scaling range that's indexed by some minimum and maximum number of vCores, which correspond to some range in memory as well, and then turn the scaling over to the service, which will then respond to provide just the right amount of resources based on the actual workload demand of the database. The second capability is automatic pausing and resuming. In this case, the user can configure what's called the auto pause delay, which represents the period of time that the database needs to be inactive before the service will automatically pause it. And while it's sleeping, the customer can assume even greater price savings. And then when workload activity returns, the database will automatically resume and become online again. In terms of billing, while the database is online and auto-scaling, it's being charged for the amount of CPU and memory that's actually used on a per-second basis. And that's to be contrasted with, say, the provision compute tier, where fixed amount of resources are allocated for a fixed price and billed hourly. Then, while the database is paused, because we've terminated the underlying compute, we're only billing for the amount of storage on disk. Now, it's important to consider whether or not serverless is a good fit for your workload, the usage pattern. If the usage pattern is intermittent and unpredictable, so for example, if there are periods of low or idle usage that are punctuated by sudden bursts in activity, then that tends to correspond to lower average compute utilization over time, which is a good fit for serverless just in terms of pricing alone. That's to be contrasted, say, with a usage pattern that's generally higher over time, in which case that workload may be a better fit for provision compute. And then also, as a starting point for new databases which don't have any usage history, serverless could be a good fit. And if it later turns out that it isn't, for whatever price or performance reason, then it can easily be moved over into the provision compute tier. And then finally, service provides all of the same PaaS manageability benefits as other databases in SQL DB. Built-in high availability, built-in intelligence, including performance tuning recommendations, and so forth and so on. Now let's demonstrate how easy it is to onboard into serverless. So here you're looking at the Azure portal. I have a logical server that's been created. It's called LS10. It contains 6 different databases. Many of them are serverless. Some of them are paused. But what I'd like to do is create a new serverless database. So I just need to click this button labeled plus create database. And then it'll bring up a page that's largely already filled out with database metadata. All I really need to do at this point is give a name for the database. Let's call it MyDB. Click Configure Database. And then at this point, you'll see that you're presented with 2 compute tier choices. You can create the database in provisioned compute, but let's instead create the database in serverless. And then finally, you'll notice that there are these 3 serverless configuration parameters that we briefly discussed. So I can adjust the maximum number of cores that the database can scale towards, anywhere from 1 to 16 cores. I can also make adjustments in terms of the minimum number of cores, below which it will never, the scaling will never drop. And that scaling range in terms of cores corresponds to a scaling range in terms of memory as well. And then finally, I can adjust the auto pause delay, which again is set to 1 hour and represents the period of time that the database needs to be inactive before it will be paused. I may want to, example, avoid pausing the database during the lunch hour, during the work week, because of the performance impact from compute warm-up. So I may extend that auto pause delay by an hour or 2. And if the database is particularly sensitive to compute warm-up, then I can disable auto pause altogether, in which case it still benefits from the ability to automatically scale between this minimum number and maximum number of cores and pay for the amount of compute that's actually used on a per second basis. So when we set out to design serverless, we wanted to recognize the independence in how CPU and memory usage occurs for the same database over time. So in this example, I have a serverless database that's configured with a max of 16 cores and a min of 2, corresponding to a range in memory ranging from 6 to 48 gigs. And it could be that at one point in time, my database may need to load a lot of data from a table into cache. And that operation may be rather low in terms of CPU, but rather high in terms of memory. On the other hand, the usage profile may evolve over time for the same database to later start performing computationally intensive operations, in which case the amount of compute may dramatically increase, but the amount of memory may be much less. So the key point here is that whatever combination of CPU and memory is required by the application, the service is ready to deliver. Another way to think about this is the memory to vCore ratio in serverless dynamically adapts based on workload demand. And that ratio ranges all the way up to 24 gigabytes per core, which is quite a wide range. And then in terms of scale-up time, suppose that the database at one point in time is using 2 cores, and then the next moment needs to suddenly increase its usage up to 16 cores. Typically, the latency for that operation is less than 1 second. There can be occasions where a few minutes of time need to pass, but that's only occurs when load balancing is required internally. And we'll talk a little bit more about that before the end of the session. Now, if you compare scaling with serverless to scaling with provision compute, it's a very different world. In provision compute, of course, the customer has the burden to specify up front what amount of compute is appropriate for the workload. So suppose I pick 2 cores, which on Gen 5 corresponds to 10 gigs. Now, one of the advantages of provision compute is that amount of those cores and that amount of memory are continuously available. There's no reclaiming of resources under the hood. You can think of provision compute as providing pristine performance dial tone. On the other hand, those resources are being paid whether or not they're being used. And then finally, if at a later point in time, the database needs more than 2 cores and more than 10 gigs, then the burden shifts again onto the customer to first identify that the database is low in resources, and then secondly, determine what a level of resources the database should be scaled toward. And that scaling process also in provision compute always lasts on the order of a few minutes. And at the completion of that operation, memories are set, caches are flushed, and connections are always dropped, representing a brief disruption in connectivity. This can occur in serverless, but only if load balancing is required, which is, again, as I said, is a very rare event. So now let's see how quickly, let's demonstrate how quickly serverless can scale. Here on the same logical server, I have already created a database in the general purpose tier. S stands for serverless, on Generation 5 hardware, with a max V core set to 8. So now what I'd like to do is run 2 very expensive queries concurrently. So each of these queries are selecting system objects and then materializing a large table with hundreds of thousands of rows, and then performing a nested loop join. So very CPU intensive. And now, if I go back here, what I'd like to display is the DMV for resource stats, which reports on historical resource utilization like CPU usage. And this will show us how quickly serverless was able to scale up to 8 cores. Right. So you can see that the workload I launched, those 2 queries, began at roughly 12 minutes and 1 second. And by 12 minutes and 26 seconds, so about 25 seconds later, that database was consuming almost 100% of all 8 cores. So again, scaling in around 20 seconds to all 8 cores from a baseline of virtually idle usage. And it probably actually scaled faster than this. Here we're only limited by the resolution of the telemetry of this DMV, which collects and reports on data once every 15 seconds. So now let's talk a little bit about how serverless works, and then just as importantly, let's connect that architecture with the customer performance experience. So serverless is a 3-tiered architecture. There's the control plane, which contains a gateway service managing connectivity, a management service that handles DDL operations like create and alter. Sitting below that is the data plane, which contains tenant rings, which are collections of physical machines that provide the compute for running all the database workloads. And then below the data plane is the storage plane, which has the database files located on remote solid-state disks. Now let's follow the journey of a serverless database, starting, say, in the paused state. So the first operation that may happen is to open a connection to the database. That connection to the gateway, first connection attempt, will fail. So it's important, if you're using pausing and resuming, to implement connection retry logic into the application. On a subsequent connection attempt, the gateway will then transfer control to the management service, which will work in cooperation with the service fabric to identify a particular machine in a ring that has enough capacity to initialize the SQL instance for the serverless database. And as part of that initialization process, the remotely stored database files become attached to the SQL instance, and at the completion of that operation, the database is then online and able to process workload. Now, from that point forward, RG Manager on this machine is constantly surveying not just the machine utilization, but also the utilization of individual databases and resolving any localized machine bottlenecks that may be occurring. And it's able to do that extremely quickly and with virtually imperceptible impact to the performance of the databases. However, if the machine becomes overloaded, then the service fabric re-enters the picture and identifies a different machine that it can rebalance one of the serverless databases to. So it will orchestrate the repositioning of one serverless workload from this machine to a different machine that can be more responsive to that rescaling. And this is an operation that can take on the order of a few minutes, as I discussed earlier, but it happens very rarely. Most of the time, the scaling is virtually instantaneous and has virtually no perceptible impact to customer workloads. Then, in parallel to all that, within the instance of a serverless database, the memory manager is constantly analyzing the usage history. And when the active cache utilization is low enough for long enough, it will begin to initiate a series of cache reclamation steps, as you can see here. Now, that's to be contrasted with the provision compute tier, where once data is loaded into cache, it tends to remain in cache indefinitely. And that provides performance advantages for queries later on that may need to access that data. They'll be able to complete more quickly because they won't have to fetch it from disk. So this represents another performance trade-off consideration when using serverless. But because serverless is reclaiming memory during these more idle periods, it's able to pass those cost savings back along to the customer because again, the billing for serverless is based on memory consumption as well as CPU consumption. So let's see what kind of cost savings are possible with serverless. Here on the same server, I have database 3, which has been running workload for quite some time. It's configured with a max of 16 cores. And as you can see in the chart on the left, over the last 1 hour, there have been 2 or 3 compute bursting episodes interspersed with relatively idle periods. And you can also see how those compute bursts are tracking with the chart on the right, which is displaying the number of vCore seconds that are billed. So the unit of compute billing in serverless are vCore seconds. Now, if I'd like to estimate the compute cost for this database over the last 24 hours, I simply need to aggregate the total number of vCore seconds over this 24-hour period. That is displayed by this metric in the lower right-hand corner. Roughly 285,000 vCore seconds have been used by this database over the last 24 hours. So 285,480 vCore seconds have been used. And if I know the cost per vCore second, which is fractions of a penny, then if I take the product of those two quantities, I'll have an estimate for the total compute cost, which works out to be roughly just north of $40. Now, if you compare that to cost in the provision compute tier for the same number of maximum cores, 16, then the compute cost over that same time period is $96. So here serverless is demonstrating cost savings of roughly, well, just north of 50%. Now, not all databases in serverless will be less expensive than in provision compute. It depended critically on the fact that this, the usage pattern of this particular database is rather spotty in terms of when it's bursting, and it's somewhat low in terms of its average compute utilization. So in terms of roadmap, we'd like to support the hyperscale tier for databases that need more I/O performance or storage than the general purpose tier can provide. We'd also like to increase the limit on the maximum number of vCores that the workload can scale to from the current limit of 16 to more than twice that amount. We're making investments in improving pausing and resuming and connectivity. For example, we'd like to lower the auto pause delay so that databases have more opportunities to cycle through pausing and resuming episodes for even greater price savings. We'd also like to build in connection or try logic into SQL client libraries to alleviate that burden from developers. And then we'd also want to provide support for availability zones to provide even greater high availability. So in summary, SQL Database Serverless is price and performance optimized for single database workloads with intermittent and unpredictable usage. And it's able to deliver that optimization by automatically scaling compute, optionally automatically pausing and resuming, and then billing for the amount of compute used on a per second basis. For more information, please visit aka.ms/SQLDB_serverless. And with that, I'd like to turn it over to Elaine for Q&A.
Fantastic. Thanks so much, Morgan, for that presentation on serverless. So we've received a couple of questions so far throughout the session. So we'll kind of start off with an easy one here. Jonas wants to know, does the time it takes to auto-scale a database depend on the size of the database?
No, I think just to clarify, I'm sure what Jonas meant is the storage size of the database. And because, as we showed earlier, the storage of the database is disconnected from where the compute is running, the scaling time is completely independent of the database size.
Yes, fantastic. And then another question that seems to be quite popular is do we need to modify any of our app settings to take advantage of serverless?
The short answer is no. You can have a database running in provision compute and move it into serverless without any application change whatsoever, and then vice versa. But I'd just like to also underscore once again that if you are consuming pause and resume as a feature, then it's really critical to make sure that you've implemented connection retry logic into your application. But that's a best practice anyway for any database, not just in SQLDB, but in the cloud in general.
Great. So we're going to take one more question here, and let's go with what is the major usage pattern that you see that fits well for serverless versus a provisioned deployment?
Right. So as I was saying a little bit earlier, in the case of single database workloads, if the average compute utilization over time is a little bit less than around 50%, and that includes both memory consumption and CPU consumption, then as a rule of thumb, serverless tends to be a good fit for pricing reasons alone. But when it comes to elastic pools, for example, the picture is quite a bit different. The short answer for elastic pools is if you have an application with tens, hundreds, or possibly thousands of databases, like a lot of SaaS ISVs do, then elastic pools tend to remain the best price optimization choice. And let me actually go back a few slides to illustrate why that's the case. Yeah. So if you can see this chart on the right, again, it's showing the a serverless database that's configured with a min vCore of 1 and a max of 8. And its usage is represented by this gold sort of jagged line that's peaking around 2 o'clock in the afternoon and then sort of gradually getting quiet again. As I said before, when the database is auto-scaling between this min and max vCore, it is and truly just being charged for the amount of memory and CPU used on a per second basis. But notice, say in the time period from 5 o'clock in the afternoon all the way leading up to 11 o'clock at night. So if you can see my cursor sort of moving back and forth here. During that period of time, the usage on the database is actually less than the number of min vCores, but it's still being charged for the number of min vCores. So now imagine I have an elastic pool also with 8 cores, and I put one database into it. Well, if I put one database into it and I'm paying for all 8 cores all the time, then I'm probably going to be paying more for that elastic pool than I will for a serverless database. But at the other extreme, imagine that I put 500 databases into that elastic pool with 8 cores. Then I'm still paying with elastic pools for just 8 cores, but I'll be paying at least 1 core times 500 databases. So for 500 cores worth of compute, as long as the database is online. Now, there are crossovers that occur in this pricing equation when the database becomes paused. So if it's paused for long periods of time, then the crossover starts to shift a little bit more away from pools and into serverless. But as a general rule of thumb, if there's any activity at all in the database so that it isn't paused, in this example at least, any single database is going to be consuming at least 1 core and being billed for that amount, which is substantially more in terms of price than what you might pay in elastic pools, where you're just paying for a fixed number of cores, regardless of the number of databases that are inside of it.
Fantastic. Thanks so much for all the great information on serverless, Morgan. Thanks everyone for joining us today, and I hope you enjoy the rest of the Build 2020.
Thanks, everybody.